Okay, so I'm recording right now. Hello, everybody. Welcome. Tonight we're doing an introduction to data science and learning about decision trees with Mr. David Elliott, one of our instructors. I did turn on the live transcript for anybody that needs it. Accessibility is pretty important to us, so I just want to make sure that everybody has everything that they need to participate in the Psycho podcast in the webinar tonight. Let's see. So just to go over a couple of rules, we're going to use the chat box as the main way to communicate with everybody. So if you have any questions, make sure that that little blue spot is clicked to everybody instead of the host and panelists, because that will let everybody see your questions. Also, for direct questions, we're going to ask you to use the Q&A. We're going to have a portion of the event where we're kind of doing okay. We're gonna have a portion of the event we're gonna want you to participate in, and we're gonna have you guys use the Q&A for that. Also, if you don't feel like answering or asking a question to the entire crowd, we can do things that way as well. Look at that, more LinkedIn stuff. Awesome. Okay. Without further ado, I'm gonna pass it over to David, and welcome.
Hello, welcome. We're going to have a little introduction into some data science and talk about decision trees, which I'm looking forward to because I love these little things. Kind of like a lot of basic building blocks, they can get fairly complex, and when used with other forms of machine learning can make some very interesting and complex algorithms that are actually in a great deal of use currently, and we'll cover some of those later. So a little brief thing about me. Oh, I probably should share the screen, shouldn't I? You can't see the slides I'm looking at. There it is. Okay. There we go. So, brief bit about me. I spent one career as a software engineer, got burnt out from all the travel of that, decided to follow my passion and spent another career as a motorcycle instructor, and then figured out that was kind of a dead end and got into data science, combining my math degree and software engineering experience and just love of numbers and poking at things to see what would happen. Decided I was missing something after I got into the industry for a little while and figured out that I really enjoyed teaching. So I've managed to combine the two as a data science instructor for Flatiron Schools, and I gotta say I'm pretty fond of it. So without further ado, let's go ahead and get in on it. Decision trees. As I said, they're really cool. In order to, can I go full screen? Sure.
Yeah, I believe if you just go to present, you should be good.
There, how about that? Thank you for that reminder. I meant to do that, but if you have any questions, please drop them in the Q&A box. We'll get to them as it's appropriate and answer them as we can. I'll definitely be willing to stick around afterwards and answer some more questions for you. So, kind of a brief overview of what we're going to talk about today. We'll have a little get to know game, which is always fun. Basic introduction to trees, look at how a computer approaches it, show you a quick example, discuss the pros and cons, kind of look at extended usage beyond that, and then we'll actually cut over to a code demo, just a real brief high level, kind of how it looks in Python using the sklearn libraries. So let's play a little game, and this is where I'm going to need your help. Hopefully you all remember what 20 questions is. I have something in my head that I'm thinking of, and I need you to go ahead and throw me 20 questions. We'll start one at a time, answer yes or no, and we will get to, hopefully, what I'm thinking about. So, oops. What is the first question? And I'm going to exit out of full screen mode briefly so I can record the questions, but I can hopefully fix that by doing that. So just for this, I'll get out of full screen mode so I can answer that. So how about the first question? It's got to be yes or no, Donnell. Yes, it is a thing. I guess we're going to Q&A. So I'll just take this last one. Can it fit in a bread box? No, it cannot.
All right.
We got, is it a concept?
Ooh. No, I'd say it's a thing.
Let's see. Try to get, says we
Does
got
it
another
have-
one. Does it have wheels?
No, it does not have wheels.
Let me see the other ones from the chat box. We got, does it have multiple colors?
I'll say, is it alive? I like that one. Is it alive? No.
Let's see.
Does it run with electricity? Yes.
Can it be used in business management? Or is it a computer?
I'm going to.
How about does
Yeah.
it make noise?
Does it make noise? Yeah. No, it does not make noise.
And
that's an
I find this in
interesting-
my house.
Oh, these are good questions. Does it make noise?
Data science audience, man.
Oh man.
Smart
Can I
group.
find this in my house? More than likely. Is it an app? Does it cost more than $100? I need clarifying on the $100. Like, what sort of? I might give things away with that one.
Will it fit in a pocket? Or does it fit in a pocket?
Well, we kind of already answered the fit in a bread box. It'll be
Yeah.
interesting to see what people's interpretation of that answer is. Does it have an expiration date? Does it have a CPU? I'll go with that one. Yes, it absolutely has a CPU. Well, this is where I gotta. I'll take that back. Does it have a CPU? No. It does not have a CPU.
Somebody asked, can it be charged?
No, it cannot be charged. Is it scalable? Yes.
We got, is it a TV?
It is not a TV, and I won't count that against things.
Okay. Does it require water?
Well, it's not alive, so probably not. I guess you can have, does it require water? No. And this will be interesting to see how you quibble with some of my answers.
Does it have branches? Is interesting. Because that could be branches of government or branches on a tree.
Can anyone own it? Is it a learner? Yes, it is a learning thing. That's a very good question. If I can spell. Yes, it is a learner.
Does it come with a manual?
No, it does not come with a manual, although there are manuals written about it. Does it only exist within something else? It is not a robot, but machine learning has a huge part in this. Is there an app that you use to control? Absolutely.
Do most houses have more than one?
Good guess on Alexa. It is not Alexa. Can it work by its own? How do I answer that question with this object? I don't watch Shark Tank, so I haven't a clue about what was featured on Shark Tank. Is it a model? It uses a model. It does have machine learning. Does it have a camera? No, it does not have a camera. It is absolutely connected to the internet.
Would
And
they train it?
Since it is a learner and it does have machine learning, you absolutely train it. And this is part of the problem, is I don't know how well some of my answers have skewed things in different directions.
Does it help clean?
No.
Got some Roomba answers over here. Can it talk?
I will say that there is to help on, does it cost more than $150? Depending on the subscription plan you have, annual costs can exceed $150. I'll try and help out with that.
I'm gonna let you pick the last one.
Yeah,
Yeah.
I'm waiting to see if there's a really good question that comes up that might help. Is it Peloton bike? It's not controlled by Amazon. I'll give you that hint it will. Does it make decisions? It does make decisions based on how it was trained. Can it recover new wall gyms? So this is a really, really good example of how I'm just going to tell you what it is. I don't think it's an ML model. So what I was thinking about was Netflix. And that's where I look at some of the answers I gave you and say, is it bigger than a bread box? Well, technically I could put it on the entirety of Netflix on an SSD and put it in there. So maybe, does it run at does it make noise? I imagine the data farms, server farms do, but not when I'm using it. Does it have a CPU? Kinda. So yeah, some subscription costs are $15 a month. So you can get it over 100. But the point of that was A, to have a little fun, and B, I don't want to do that. I want to go to that one. And B, this is actually an excellent example of A, how a decision tree works, and B, how if you don't feed it the right information, it can go offline. It can go off in a corner and go, wow, we went down a wrong path. So let's go a little, yeah, how a decision tree failed, exactly. And it didn't work that well. Part of it was probably because of some of my answers. I didn't give the best answers there. But let's look at and we will come back to what happened here, by the way. So let's look at this. Here's another example of how a decision tree will actually look at something and predict an outcome. In this case, it was from the from a couple elections ago. And will a county go for Obama or Clinton? And I don't know how well you can see this, but it just looks at these questions here. Is the county more than 20% black? Yes, no. Obama won those counties that way. No, and it just kind of works through these questions, trying to get a better and better, closer to an answer. So here is an example of a decision tree making a prediction kind of in real life. So hopefully this will help show how it looks like a tree is. It's kind of a sickly tree, but it's also a little bit different in that our computer decision trees start from the top and grow down versus growing up. Let's talk about some of the vocabulary of a decision tree. You have a decision node. The main node's the first node. After that decision node, the main primary node, you go into these other little decision nodes, and those will either lead to a leaf node where it ends with your prediction, or it can go into what's called a subtree that you can then do a decision node or a leaf node. You can predict. This is a binary classifier, and what we're talking about here is we're simply going to do binary classifiers. Abdul, you can absolutely use a decision tree to classify more than one class, but such multi-class decision trees are going to be a little beyond the scope of what we're talking about here. How a computer goes about making these decisions. Information gain, entropy, is one of the formulas. Let's see if it'll show it. Yeah, you can show. There's all kinds of math. I linked to the math, and you'll be getting this stuff later. But information gain is one way of determining how to get a what node. And if you recall these questions, this is exactly how you were approaching the "what is David thinking of" question. You were trying to figure out, gain more information, increase what you knew about it based on each of these questions. And yes, I agree. Can it be charged? Yeah, well, and then I wavered on. Anyway, you see the idea there. And that is one way of a decision tree gaining. This is a kind of a outmoded, and it's not used that much anymore. Slower to use. It's also bound by 0 and 1 for the computers. Gini impurity score is what is generally used. And the Gini, some of you may be familiar with the Gini coefficient from finance. It's unfortunately the same name, a completely different concept. The Gini impurity score looks at the decision point and figures out what decision point will have the purest result. So if I were to look at this slide, the decision tree is going to make a decision based on which of these leaf nodes is going to be able to have the purest result, or the littlest overlap between the two classes. So a perfect Gini score is going to be 0, and it's going to have like all one class here and all one class in the left, and the other class in the left node. That is what we'll be using for the decision trees I'm going to show you. So one other thing that's interesting about decision trees is they use what's called a greedy algorithm. A greedy algorithm does not take into account the whole of the tree at all. It looks at that decision node, this single decision node, and tries to figure out the best possible split. It doesn't care about any other decision node in the tree. It looks only at that decision node, hence the term greedy in terms of greedy algorithms. There can be some issues with that. It does lead to overfitting, which we'll talk about in a bit. So basically, high-level overview of how a computer looks at figuring out what decision point to make.
We have a couple questions if you wanted to. They were asking, are decision trees bias? And then somebody asked to see the previous slide.
Hopefully I showed you the previous slide enough. Are decision trees bias? I'm going to be honest, I don't quite understand. Are you asking if they're high bias or high variance? Are you decision trees are prone to overfit, so they tend to be more on the higher variance side unless you prune them or tune them properly. Not certain if that's the question you're asking, and if not, please ask a clarifying question and we'll get that information to you, or try to. So to show an example of a decision tree that's a little bit more understandable, this is the Titanic data set. 891 people on there. Our target, what we're going to try and predict, is survival. Did they survive the Titanic? It's going to be yes or no. And these are just a couple of the features or bits of definition or bits of information or columns, if you're more familiar with databases, that we're going to use. We're going to look at the passenger class, and it's going to be a 1, 2, or 3. We're going to look at the gender of the individual, 0 and 1. And where the other thing that's going to be looked at is the port of embarkation, which is kind of an interesting thing. And a question. That is a disadvantage of the decision tree. You tend to keep it in memory. So we run that and we end up with something that looks like this, and you're looking at this going, what in the world was that? That is an example of an overfit tree. That's an example of it's trying to figure out exactly every possible little case. You don't ever really want to see something like this. This is an example of a much better tuned tree, and I just kind of wanted to step through what it's looking at. The computer, for its very first primary algorithm, looks at, yes, I will start doing that, Melissa. The computer algorithm looks at this and looks at all the features we give it, the age, the passenger class, where they embarked, et cetera, and it looks at each of those to try and figure out how it can get the best and purest score, the Gini score. So if you look at this, the best it could do is 0.473, and that's not really good. Gini scores go from 0 to 0.5, 0.5 being bad, 0 being good. And it's saying in this decision node, it looked at all 891 samples and it was able to divide them into 540 in the 0, which is did not survive, and 342, which is the yes, it survived. So it then took those and split them further. If the sex of the row, the observation, the individual was less than 0.5, i.e. 0 in this case, because it's a 0 or 1, it goes to the left here. And this is just sort of there's no rhyme or reason about whether it's true or false, which way it goes. It's just that they chose true as left. Could I explain the Gini parameter again? The Gini impurity score looks at all the samples and tries to figure out, let me take that back. The Gini impurity score looks at this split here and gives you a result. It's not quite a ratio. There's some more complex math behind it that when you get the slide deck, you can go read the Wikipedia article. But basically it tells you how pure that sample is. To split down really quick here, we can look at this bottom one and say the Gini is 0 because it was an absolutely pure split. It had nothing of one class, the 0 class, the did they die, and all of its samples were in the 1 they survived class. So that's why this is a Gini score of 0, as pure as possible. What the computer is doing is looking at the Gini score that's calculated from each split and tries to find the most pure split. And so for this case, it was this. Is parent the root node and everything else child node? I understand child nodes are separated by decision and leaf, but there seem to be many. In this example, this is the parent node, the main node. Here are 2 decision nodes off of that. Each of these decision nodes goes off into 2 more. All of these items on the bottom would be considered leaves. It is not quite, it's not an exact ratio of one to another. There's some more information, there's some more calculations that go into that, but that's a reasonable way of thinking about what the Gini impurity ratio is. So we have everything that gets split off here, and now what this diagram is telling us is saying, okay, I went through all the different things and said, cool, you know what? I got the best, the most pure split at passenger class less than 2.5. So basically, class 1 and 2 are over here, class 3 is here. So if the passenger class was less than that, the trees, based on what aspect does the tree do the split, the lowest Gini score it can find. It runs through a number, it runs through pretty much all the features and tries to figure out which feature is the best and then what split. The math behind how it calculates the features and how the computer finds which features and finds what split point is kind of beyond the scope of this class. But that's what the algorithm does. It steps through everything, comes up with this bit of information here. So for these 340 for these 314 samples, it is saying it got the best split using p class less than 2.5. Then it says the values of these two, the 81 and 233 add up to 314. That's saying that's the 0 prediction and that's the 1 prediction. Again, 0 did not survive, 1 was survived. And then if it was less than that, you can see, you can go down here, and then now it's looking at age. And here is one interesting thing. Each decision node, and this is an example of it being a greedy algorithm. So if we did the false, i.e. they were greater than 0.5 or male, it comes down into here and looks at this one and then says it's going to split on age. This decision node looks at P class. Okay, cool. This decision node also looked at P class. So it does not matter. Each of these nodes have no effect whatsoever on the other nodes. And that's, again, showing you an example of a greedy algorithm. So at the end of it all, with this slightly or lightly tuned tree, it comes down to these leaf nodes. And you can see as an example of this was the best it could do. And the final Gini impurity score of this is 0.5 because you have one of each class. This is a much better split, so a much lower Gini score. So this was how to read a tree. And this is one of the nice things about decision trees is you can create a printout like this, and it's very easy to look at what features it's looking at, how it's looking at them, what the scores are. It's very interpretable and fairly easy to understand, which is a significant advantage of decision trees over other models. Briefly, and I know there's a whole lot of text here, and I apologize for that, sort of an advantage and disadvantage of pros and cons of each of them. Trees can be used for not only classification, but regression as well, i.e. predicting like a house price, a more continuous variable, whereas classification is literally what class are you a part of. Obviously, you can see that they're graphically displayable, highly interpretable, and hopefully the failed 20 question game showed how they can closely match human decision making. It is a very quick algorithm, even though it seems like there's a lot of computations going on in terms of which feature and whatnot. In the grand scheme of machine learning, there's not that many, and it's quick. It's a very, very quick thing. Another advantage is scaling, because, and this is a little outside of the scope of this course, but for those of you who are a little more familiar with this, we don't have to scale the features of a decision tree. The scope or size of the feature has no effect. Whereas if you used other algorithms like linear regression, logistic regression, or k-nearest neighbors that use a distance-based algorithm, the size of the feature will have an effect on there. pretty quickly they will ignore irrelevant features. I mean, you got a view of that here. It only looked at the sex, the age, the class, and if they embarked from Southampton or not. Everything else the model deemed as irrelevant. It's like, that has not helped me. I can ignore it. And in cases where you have a not lot of non-linear features and response, that will the model will still work fine. Some disadvantage: there are better supervised learning methods out there, and decision trees are actually the foundation of some of them, and we'll cover that in just a little bit. And as you saw from the previous one, it's really easy to overfit the data. This decision tree was trained on the exact same data set that I did the trimmed tree on. I just basically let it go until it ran out of steam. So that's an example of how very easily overfitting. And I talked about tuning, and what you tune and how you tune a tree is, again, beyond the scope of this class. This is where things get interesting. Trees can be a little bit rigid. So if you have differences in your data, it can cause for a different decision tree based on your training data, making them highly variant. That is solved with some other methods that we're going to talk about in just a little bit. This type of recursive binary splitting, the locally optimal, the greedy algorithm, that may not be the best overall tree, so that's a downside of this. And another issue is highly unbalanced classes. That would be an example of, for example, say a cancer test. I have 9,999 examples of where it's negative and one example of where it's positive. That's a very imbalanced class. Decision trees don't work well on that kind of data. And they also don't work well on really small data sets. 891 records, observations is a pretty small data set, and doesn't work that well. So a high-level overview of the pros and cons of decision trees. But decision trees, for all their faults, can be used to build the basis of three much more powerful and active and used algorithms. The first one is bootstrap aggregation, also referred to as bagging. And basically, you're taking a whole bunch of trees, feeding them all a small sample of the data, and it's with replacement for those of you who are familiar with random sampling. So it's a small sample of the data with replacement. It feeds it into a whole bunch of different decision trees and kind of votes on the answer at the end of that. How does it look at the end of that? Accumulates and aggregates all of those smaller trees into a hopefully much better predictor. Even better than that is boosting. Boosting, again, will take a random subset of the data, again with replacement, but it looks to see how it did, and if it had more errors, it will weight the data appropriately. And at the end of the day, it then takes all of the weighted data and creates a final decision tree out of that, and they're generally much more accurate than either bootstrap aggregation or just a plain decision tree. And my personal favorite, just because it amuses me so much, are random forests. Random forests take a whole bunch of small trees, feed it a random sample with replacement of the data, and they also take a random sample with replacement of the features, of all of the features of the data set. So one tree, in this example, the Titanic, one tree may get 50 rows with all you have is sex and P class. The next tree may get 50 different rows. They're just fun, Abdul. They're incredibly powerful. They're very resistant to a lot of the features that affect. What do I mean when I say replacement? That is bootstrapping a data sample. What that means is if I reach into an urn with 3 different kinds of marbles, I'm going to reach in, grab a handful, pull it out, and that's my random sampling of marbles. Now, if I want another sample, what I mean by when I say with replacement, I will take that initial sample that I pulled out, put it back into my urn of marbles, and take another sample after mixing it up. So I'm always drawing from a full set of data. So it's not grab a handful, pull it out, leave it out, grab another handful, pull it out, leave it out. So that's what I mean when I say with replacement, random sampling with replacement. So back to the random forests, it takes the example I had was one tree had maybe sex and passenger class. Maybe the other tree is going to have age and embarkation from Southampton. The other one's going to have P class and ticket or something like that. So it takes all of these little smaller trees. Some of them are actually called stumps, which is kind of a fun term because it's literally one node and 2 leaves. So it you can print them down. So you just all these little stumps of data, puts them all together to get a fairly robust and really good classifier or regressor. So random forests are one of the more they're used quite a bit actually out in the real world. The downside of random forests is that you of course lose any interpretability because you've got no idea how to do that. I think I've got caught up with all the questions. I'm going to pause here, see if there are any more questions that come up. What I would like to do with some of our remaining time is jump into I have a small little Python demo, just kind of showing you what it looks like from Python side using sklearn. The GitHub repo, that's nice, David. The GitHub repo will, Jelani, are you going to Slack that out, or Corey?
I will put that in there right now.
Okay, thank you. You can either clone it down if you've got Jupyter instance and installed on your local machine, or you can click on the binder and that will launch a binder session. So what I'm going to do now, those do take a little bit to spin up. So I'll take 3 minutes now and wait for questions and let people either clone that down to their local machines or open up a binder link, and that way we can all kind of work through this together. So I have 7:42 Eastern time. So at 7:45, I'll get going again and step through a little brief overview of the code. In the meantime, if you have any other questions, please get them up. Correct. Decision tree is true or false. It's yes or no. The decision tree comes to a decision point and says, oops, you can't see that because I'm there, and says it's either true or false. You get better data, Ananth. Hopefully, I'm sure I butchered that and I apologize for that. Data problems, there's no model in the world that will solve a bad data. Garbage in, garbage out. Decision trees handle missing data. They don't care. They don't give a hoot about nulls. That's the nice thing. You don't have to really worry so much about missing data. They're like, okay, whatever, and it moves it on. There, hopefully that will be big enough people can see. How does the decision tree know which element to select while performing decision? That is a very good question, and the math behind that, you're going to have to delve in on your own. There are, it's frankly beyond the scope of this class to talk about how far down, that is getting really far into the code of the decision tree, and we're not going to talk about that in this class. Just this is where I say, trust me, the algorithm is choosing the best possible element to select. That is a very good question. Threshold size for a trees database. don't know kind of what, honestly don't have a really good answer for that. I'd have to look at sort of what a minimum is.
Somebody had a question about the link, whether it's like binder or launcher.
It's the same thing. It's that link launches the binder, so there's no two links to that. It's one button. Link. And you'll get something that looks like this, and it spins it up. Oh, look at that. In order for decision trees to work, are values automatically treated as Boolean values? I think what you're referring to is what we had to do to the data to prep it. Is that what you're talking about in terms of a Boolean value? Survival is this way. A decision tree needs numbers to work. So we've got to figure out some way of turning those text values into numbers. And that's so this isn't Boolean, it's 1, 2, or 3, but it's still a number. The decision tree itself is a Boolean decision. It's either true or false. I don't know if that answered your question. And the other question, why do we use this GitHub? This GitHub is literally this code with the data behind it to run it. So I can show you a code sample and you can have access to that. That's why we're using this. You click on the link. It's going to end up with something like this. If you click on the link, you're going to come up with this GitHub. You can click on the launch binder and you will end up with something that looks like this. Then you just double click on the decision trees info and you can follow along without having Jupyter or any kind of anything installed, because this is entirely on the server side. I'm going to step through the code here kind of briefly just to make sure you're following along. We're going to use our pandas libraries. We're going to use our plotting libraries. Here is the library we're importing the decision tree. It's from the tree family in sklearn. And for those of you who have a little familiar, I'm also going to be showing you a bunch of just scores so you can look at the classification just kind of for the heck of it. Is Binder running on my computer or their computer? Binder is a Docker container running on their computer. All you have is a web browser. It's literally a browser page and that's it. There's nothing locally running on your machine. So and this is just a really quick little function to print out all the scores so I don't have to keep typing it in every time. What we're doing in this data is that I'm creating my pandas data frame, which is kind of like Excel for Python is the best way to think about it, or maybe Access for Python. I haven't really thought about that, but it allows me to manipulate the data pretty easily. Call it Titanic, and then I'm accessing the sex column and changing it to 0 or 1, depending on if it's male or female. I am going to, just to keep things consistent, replace any null value with the median age. And there's lots of debate about if that's a good, appropriate way to do it or not, but that's also a very different class. And this is where we create a binary column from the embarked. Embarked was either Southampton, and now I can't remember it was Southampton, Queenstown, or Cherbourg. So that will basically create a dummy column where it's 0 or 1 in embarked underscore C, embarked underscore Q, like you can see that. So it takes the Cherbourg, Southampton, or Queenstown and puts a 0 or 1 there based on where they're embarked, and that will turn that text into something we can use. And then it puts it all back together into one thing, and this is what it looks like. We have do they survive, what their passenger class is, sex, their age, and this is what I'm talking about when it embarked. So it's either Southampton, Cherbourg, or Queenstown, and you can see if they embarked in Southampton, they get a 1 in embarked S and a 0 in embarked Q, and that way we can turn a text value into something that the model can use in terms of a 0 or 1 or a number. We're going to just look at these feature columns. No particular reason other than this is what worked for the model. It's like, we'll just pick these. There's no rhyme or reason to that. So I'm creating my X data, or what we train the model on, from the feature columns, and the Y, or our target, what we're trying to predict, is from survive, which is that 0 or 1 column. So this is that massively overfit tree I showed you all earlier. And basically I'm saying, don't do any tuning at all. Let it. I'm going to let the algorithm figure out when it's done, and this is what we get. But, and those of you who are from, oh, it's because I didn't run this. Sorry. There we go. Let's try that again. We have those of you who are familiar with this, a confusion matrix here. This is the true positives of, we predicted they survived and they actually survived. We predicted they died and they actually died, and false positive and false negative. So just for those of you who are familiar with those metrics, just kind of showing you the difference between how this tree is got pretty good accuracy, pretty good precision. It's really overfit to the data. To answer your question, how reliable? I'm not certain reliable in what way. They'll work with whatever data you give them. The size of the data set has sort of a lower bound. You want a couple thousand records to really be able to let it train, but very large sets of data. And now the question becomes, you need to define very large sets. Megabytes, petabytes, exabytes. How big a data set are you talking about? For a lightly tuned lightly tuned tree, this is, I say, set max depth at equal to 3. So it only goes 1, 2, 3 nodes, and it calls hop and stops there. But as you'll see, it's not as accurate. So I'm going to have to scroll up so you can see. I should have put these beside each other. You know what? I can do exactly that. There, I will put the two confusion matrices beside, and you can see how not as accurate on who survived. It didn't do as good a job there between the two trees. This is the one with the max depth of 3, lightly tuned tree, like I called it. Here's the other one, and then I'll just do this. CLF in, there we go. So you can see it's not as accurate, it's not as precise. The recalls a little better in this one, but it's just this is the end tree where I did anything. Why is overfit a bad thing? It's okay in the time case. Yes. Why is overfitting a bad thing? So how much time do I have? I think I've got
over
time.
a little bit. It's okay.
Okay. Oh, I will get back to that question, June. Not June, but Donnell. So let me show you the other thing that's pretty cool about a decision tree is that I can create a data frame, and it says, it will tell me it looked at these features. Well, these are the features we gave it. And this is the importance, the relative importance of each feature. So sex had the greatest importance on whether a person survived, which when you look at the data, it's absolutely true. Vastly, I think it's 2/3 to 1, 3/4 to 1. Vastly more women survived than men. So the decision tree rightly picked out that, oh, hey, sex is our most important feature when it comes to if they survived or not. But this can be really handy when explaining what a decision tree does. How did I conclude that the second one was not great? This is a better predictor due to the classification. This is the second one where I had no max on the number of nodes. This one is the first one where I had a max of 3 and the accuracy score is less, the precision score is less. So just looking at the metrics. Now, to get back to Donnell's question, why is overfitting a bad thing? This is a broader topic, and it starts with how you train a model. So the brief overview is I take the data I'm going to use. And if I had been doing this accurately and correctly, I would have split the data out into a training set and a testing set. If I overfit on the training set, and pretty much what Abdul just said there, overfitting means it'll just learn that specific case scenario really well and only do that case and do poorly in other cases. We refer to that as generalization. If I overfit on a model, I have figured out so well how my training data works when I take that trained model and feed it data it hasn't seen before. The model goes, I don't know, there's nothing here, and it does very, very poorly on the predictions. So that's why overfitting is a bad thing. I may train the model to be very accurate on the training data, but when I introduce new data to that model to say, hey, make me a prediction on this new set of data. An example might be something like, housing prices. I have all these houses I've trained on, so it learned all of the features. Okay, it makes sense. So I will stop babbling then and trying to explain it more. Good question though, and that's something that we delve into greatly when in our data science course, because it is an important thing to recognize. It's an important thing to see and figure out and how to deal with it. It's better to have and there's a whole debate between statisticians and data scientists too about predictability versus interpretability. That's always a lot of fun to get into. Any other questions? We have some time, so you've been pretty active about bringing these questions in, but definitely, is there anything else I can answer or anything else you'd like to know about decision trees? To get back to your question about how reliable is decision trees on data, the decision tree is as good as the data you feed it. Sort of a mantra in machine learning is the more data, the better off you are. So if you have a whole bunch of data, feed it as much as you can, as long as it's good data. And another question, is there an app to create a decision tree with? I don't know of one off the top of my head. I quite literally created a couple decision trees here. What fraud is a big one where it's used in fraud because we're random forest. Decision trees themselves aren't used a whole lot for a lot of the reasons I explained. I mean, they're kind of fun for exploring and looking at feature importance, but when you get to things like random forests are much better at teasing out subtle patterns and handle things like feature imbalance really well. And so I know fraud detection, random forests are used a lot in fraud detection, for an example. Can you outline it visually to make sure you don't miss an option? I'm not certain what options you're talking about, so maybe clarify that, Kimberly. Is there a problem having more predictor values than there are data points? Oh, can you define the element to make the decision? No, that's the magic of the algorithm. It figures out based on your parameters which feature is the best one, feature or element is the best one to make a decision on. Like with linear regression, is there a problem having more predictor values than there are with data points? Well, each row has a prediction. Oh, I see what you're talking about. It's not nearly as bad. It can affect things, but then you talk about, so what, let me clarify her question, make sure I understand. Predictor values, i.e., For us in this Titanic set, we had passenger class, sex, age, ticket, fare, cabin, et cetera, et cetera. And there are data points, rows or observations. So do I have, to break it down, do I have more columns than I have rows? There are models that work better with that kind of thing, but you generally gonna want a lot more rows than columns. You want a lot more observations than, excuse me, features. Cool. We managed to end right at 7.
Oops,
You're muted,
sorry, I'm
Corey.
muted. Yeah, there we go. I'm on mute. I just wanted to say thank you guys for coming out tonight. This was a great thing. Thank you, David. As I mentioned earlier, this is going to be sent out about 48 hours after the presentation, and we will send it to your email address that you registered with. You can also find it on our YouTube page, and it's probably going to be Monday. So thank you everybody for coming out, and have a wonderful evening. And thank you again, David.
Thank you all. I really appreciate the question. That was a lot of fun. Thank you so much.
Bye, y'all.